Now that we've covered how to show that a limit does not exist by the use of paths, now let's talk about how to show a limit does exist. So all of the rules that we have from Calc 1 are currently in play except for L'Hopital's rule. We're not allowed to use L'Hopital's rule to show that a limit does exist because we do have multiple variables in these limits. So one of the things that we have from back in the day is referred to as the direct substitution property. The direct substitution property is a fancy way of saying try plugging in the point that we're approaching. If it works and it's not in a determinate form, then you're done. Don't count on this one working right away on these problems too frequently. So a direct substitution property would really be something like this. The limit as xy approaches 1, 2 of 5x minus 3y. The direct substitution property says, let's plug it in, see what happens. That would be 5 times 1 minus 3 times 2 for a final answer of -1. The direct substitution property is awesome. It's also incredibly boring as far as problems are concerned, so don't expect to see that one work right away too frequently. Second possibility is algebraic manipulation. So algebraic manipulation could come from things like eliminating fractions inside of fractions, that is simplifying complex rational expressions, multiplying by the conjugate of a radical expression, all sorts of things that could have existed from way back in the beginning of Calc 1. So limit as xy approaches 0, 0 of, let's do the square root of x squared plus y squared plus 1 minus 1 all over x squared plus y squared. In this case, if you attempt to use the direct substitution property, red means danger on this one, and we do plug in 0, 0, we'll get 0 squared plus 1 under a radical, minus 1 for 0 up top, and 0 squared plus 0 squared in the denominator for a total of 0. Now, we are going to perform an algebraic manipulation here, and the algebraic manipulation that we are going to perform is something I mentioned just a moment ago. We're going to multiply top and bottom of the big fraction by the conjugate of the numerator. Anytime you have a square root plus a number or a square root minus a number, well, in this case a number, more generally an expression, you can get rid of said radical by multiplying by the conjugate. The conjugate is what you get by changing subtraction to addition or addition to subtraction, as long as it's the term that's outside of the radical connecting those two things together. Reason being, if you take something of the form a minus b and you multiply by a plus b, you're going to wind up with a squared minus b squared. As I frequently say at parties when I go to parties, is that a product of binomial conjugates will be a difference of perfect squares. I believe I just let you know why I don't go to a lot of parties. So put it all together and we will get the first radical, or rather the radical, squared minus 1 squared. Our denominator is just fine the way it is, so we're going to go ahead and leave it as is. Like so. Looks like I was a little overzealous with how long that fraction bar was. The good news is, up in the numerator, once we square the radical, the square and the radical will cancel. We'll be left with x squared plus y squared plus 1 minus 1. So what I'm going to do is simplify that numerator through those two steps. Those two steps being cancel the radical and combine like terms. What we're left with up top is going to be x squared plus y squared. And in the denominator we will have two things, x squared plus y squared, as well as the square root of x squared plus y squared plus 1 plus 1. We can cancel out the x squared plus y squareds, leaving us with the limit as xy approaches 0, 0 of 1 in the numerator, and in the denominator our radical plus 1. Once you've made this manipulation, it is now going to be possible to use the direct substitution property. leaving you with 1 over the square root of 0 squared plus 0 squared plus 1 plus 1. So final answer for this one would be 1/2. You'll notice at no point in here did I ever mention that we were going to use a path or anything along those lines. In fact, if you were to use a path and repeat this process, you would wind up getting 1/2 every single time. Unfortunately, paths cannot show that a limit does exist. There is one other possibility, and it's for a very specific kind of limit. And that would be by using a conversion to polar. Now, we know that conversions to polar come in a couple different forms. We have our 3 major conversions into polar coordinates that we like to use. X squared plus y squared is equal to r squared. X is equal to r times the cosine of theta, and y is equal to r times the sine of theta. The reason that this is significant is if you have a limit as xy is approaching 0, 0, this is equivalent to the limit as r approaches 0 from any direction. Now, that said, we can constrict it so that we're specifically talking about a case where r is a positive number, despite the fact that we are going to be approaching on an actual path through the origin. So this is due to the fact that theta is technically equal to anything as we pass through the pole, or the origin, as it were. So I'd like to consider the following. Limit. I'd like to do the limit as xy approaches the ordered pair 0, 0, and let's do x cubed plus y cubed over x squared plus y squared. Now, you can try paths for this one to try to show that it doesn't exist, but you are going to get the exact same value every single time. Additionally, we should do this one in red because red indicates danger. If we attempt to use the direct substitution property, you are going to wind up with 0 divided by 0. Now, with that in mind, if we do a conversion to polar, we can now express this as the limit as r approaches 0 from the positive side of. For the x cubed, we'll use this conversion into polar. That'll be r times the cosine of theta, quantity cubed, that's not how you spell 3, come on, plus y cubed, we'll use this conversion for y, r times the sine of theta, quantity cubed. And for the denominator, we'll go ahead and shortcut our way to this conversion right here. We'll call that denominator r squared. Now, through the use of a little bit of factoring in the numerator, we can refer to this as r cubed, being the greatest common factor, and call this cosine cubed plus sine cubed. This will all be over r squared. So with that in mind, we can reduce the fraction. R cubed divided by r squared will reduce down to the limit as r approaches 0 from the positive direction of r times the cosine cubed of theta plus the sine cubed of theta. Now here, in order to actually evaluate this limit, we are going to need to use a squeeze theorem. We're going to need to use the squeeze theorem argument. Excuse me, that's the phrase I wanted to come up with. So I'm going to be even more liberal with the bounds on this than I have to. The largest value that the cosine and the sine can each take on is 1. So cosine cubed of theta plus sine cubed of theta is most definitely going to be less than 1 plus 1. By a similar argument, there's no way that they can be less than -1 each, so the lower bound would be -2. Now again, the actual restriction on this is much, much more conservative than this, but that's fine. This also lets me know that -2r is going to be less than or equal to r times the cosine cubed of theta plus the sine cubed of theta, which will be less than or equal to 2r. Then, if we let r go to 0, we can make use of the squeeze theorem as 0 will happen on the left and 0 will happen on the right. So by the squeeze theorem, the limit as r approaches 0 from the right of r times the cosine cubed of theta plus the sine cubed of theta is equal to 0. So these are just 3 different ways that you can show that a limit does exist and find out what it happens to be equal to.